Alright, so this next part is going to have us test the claim using a confidence interval. So what we need to first do is, well, find out what is the formula for a confidence interval for two proportions. So what we're going to do is I'm going to snip this, and we're going to, let's see here, was this question 3? Question 3, we'll say like question 2. And confidence interval. So here's the general formula again for a confidence interval comparing two proportions. I'm going to snip that and paste. And we're going to have minus okay, here is our confidence interval formula. It's, well, we're not quite done yet. Just a little bit different. And 1 minus. All right. So the main thing I want to point out, and this is kind of why I showed you me typing it out, is, hey, notice this time what we have here inside of this confidence interval formula is that we've got our P1 hat and our 1 minus P1 hat over N1 now, our P2 hat and our 1 minus P2 hat over N2. And that's kind of interesting because here in our z-score we use a P hat of C distributed outside of both, and we kind of talked about how it's distributed outside. It's really over both of those numerators. But here, I don't have a P of C. And let's remember why that is, because ultimately a hypothesis test has a null assumption. And so we need to find a way to compare to the null assumption. These should be equal. I don't know what it should be, so let me match these two values together to get my best estimation of what this should be if they were equal. Combine these two. Any difference I see is just noise. This should have been what I should have gotten if they were both equal according to my samples. And so now let's see how different they really are. But a confidence interval doesn't have an assumption to it. A confidence interval says, let me strictly use sample data and see what I get. So we get this new formula. So let's walk through typing in this formula to the calculator and then see what we can conclude about this. So we've got the majority of the work right here. I can still start by doing my P1 hat. And really I'm just reading from the top of my test statistic because the top of the test statistic actually has a lot of the data I need. 2829. And I guess I'll do the subtraction first. And now I'm doing a confidence interval, so I need that z value for 95% confidence that lives at the bottom of the t-table, so 1.96. This is the same thing we did earlier in earlier chapters. Now I need that big ugly square root, and it's going to be the 0.2952 times its complement, 1 minus 2952, and divided by its sample size, which was 1423, plus, oh goodness, now the 0.2829 times 1 minus the 0.2829 divided by its sample size, which was 767. So that sure is a lot to type in. You definitely want to make sure you read it carefully when you type it in. Of course, I am going to show you where this lives in the calculator so that you don't have to do all this work, but again, there are many other classes where this is what you must do. So there's my confidence interval for the left value because I did the subtraction first. It's negative 0.027 to 3 decimal places. After all that hard work, trusting that I typed it in right, I just need to change that minus sign to a plus sign to get the upper bound. And now I get 0.052 to 3 decimal places. Awesome. All right, so we learned how we can use a confidence interval. Now, it says, what conclusion can we make based on the confidence interval? And so, although a confidence interval and a test statistic are doing different things, one's using a P of C, one's using only the sample data, they are ultimately still both trying to infer about the main population. So what was the inference going on here? Well, again, the null hypothesis said my two values should be equal, or in other words, remember the test statistic. When I compare these two, I'm comparing it to 0, because two subtractions, or a subtraction, if two things are equal, should be 0. That's what the null says. And the alternative was just, are they different? Because it just said they think it could be different. Is it equal or is it not? Now, my confidence interval is also kind of focused on what is the comparison and is it 0? Because, well, there it is in the problem. But because the confidence interval limits include 0, or in other words, because my 95% confidence interval says I've got some negative values and some positive values, that means my confidence interval contains 0. Or in other words, with 95% confidence, it's plausible that the difference between these two is 0. Or in other words, that they are the same, which must mean that they are not different. So the confidence interval says 0 or no difference is possible with 95% confidence. Therefore, the null is possible with 95% confidence. So that means there does not appear to be significant difference between the two proportions. There is not sufficient evidence. So if your interval contains 0 or no difference, that's equivalent to saying there's not sufficient evidence, because again, if we're 95% confident that the difference between the two is nothing, then that means we're 95% confident saying that these two could be the same, or in other words, what the null says. So we can't reject the null hypothesis if my confidence interval shows that these two could not be different. All right, before we run through the rest of the homework, I think it's going to kick me. Oh my goodness. The confidence interval suggests there's no significant difference between the success of men and women. I think we're going to go with B. Great. Are we finally done with question 3? Yes, we are. All right, before we go through question 4 and question 5, what we're going to do is run through this example, again, showing you how to do this all in the calculator, and then we'll just live in the calculator from now on as we do the rest a little bit more quickly. So to run this through the calculator, we would go to Stat, we would then do Tests, and we are going to do a 2 proportion z-test because we're comparing 2 proportions. And let's see here, there were 420 men, there was 1,423 calls, there was 217 women whose calls were overturned from the 767 sampled, and we were testing that they were not equal to one another. And look at that, that's all of the work with so much less effort. There's the z-value, there's the p-value, there's the individual sample values that I was using, there's the combined c that I found. So everything I did is sitting right here on the calculator, but it's so much less effort. So yes, by all means, use these formulas, but I just wanted to review what happens at a two-tailed test. How do we do this by hand? I think there does need to be some sort of appreciation for doing this because, after all, again, many other college students have to do this by hand, so to speak. They have a calculator, but it can't mash the data out like that. Now, we also found a confidence interval, so we could scroll down and somewhere there, 2 prop z interval. All right, well, it actually uses all the data you used last time, so that's nice. It already knows you're probably using that data again. It was a 95% confidence level, and look, there were the same values to 3 decimal places. Actually, I guess because of the precision, that one's a little bit interesting. They must have rounded that 4 up to a 5, which might make you think to round that 7 up to an 8, so maybe there's something to be said about just doing this by hand. But that would be something negligible that I wouldn't care about on an exam. So just be careful. The technology is more precise and may lead you to round up or down a little bit differently than by the tables, which is what the homework kind of goes off of. All right, we've done the heavy lifting. Let's do number 4 in the calculator and show you how fast these problems can be now that you have the calculator. So we've got front seat occupants in car crashes, and people who were not wearing seatbelts and people who were using seatbelts. And we want to claim that seatbelts are effective in reducing. So let's see here. We think that seatbelts reduce fatalities. And notice that the people who were not wearing seatbelts came first. So if the people who wear seatbelts reduce fatalities, we would suspect that the second proportion is smaller. That looks like F. We need equality. So again, that automatically brings us to just B, E, or F in our nulls. And we wanted that the people who wore their seatbelts to have a way less significant proportion of deaths. So there we go. After that, let's use the calculator and run through this question really quickly. So stat 2 prop z test. And our first population had 34 non-seatbelt wearers who passed away out of 2,835. And for the seatbelt wearers, there were 13 deaths among 7,772. And we are, of course, again, testing that the P1 is greater than P2. Sometimes this does look a little bit weird on the calculator, but just know that literally read the computer alternative and then make sure that the inequality is going in the same direction and you are safe. All right, and we'll press calculate. So we get a z-value, a very large z-value, 7.08. We then get the p-value, because that z-value is large, this p-value is very small. To 3 decimal places, that's going to be practically 0, because I should have 13 leading zeros. And so the p-value is definitely less than the significant level of, notice this time it's 1%, but it still beats that out dramatically. So we definitely reject the null hypothesis. There is significant evidence or sufficient evidence to suggest the fatality rate is higher for non-seatbelt wearers. So there's the lesson we've learned today. They want us to do the confidence interval. Again, here's how quick that can be. When I scroll all the way down, instead of 2 prop z test to 2 prop z interval, the confidence interval already has the same data set up. Be careful though, if alpha was 1%, and this is actually a little bit interesting, since alpha is 1%, the confidence level I need is 99%. So your confidence level comparison is based on the complement or the opposite of your alpha. So when alpha was 5% in the last question, that's why we used a 95% interval, because 5 and 95 add up to 100. Now that I have alpha 1, I need 99 so that I add up to 100. I calculate, there it is. Let's hope we don't run into those pesky rounding situations. I think we're safe to 3 decimal places. 0, 1, 5. That'll round up to 6. Okay, now this one's also a little bit interesting. We need to talk about this carefully. The idea this time is, even though these numbers look really small, and they are small because evidently, how do we say it? Whether it's people wearing their seatbelts or not, evidently it is just rare in general to have a death in a car crash. All right, that's what P hat of 1 and P hat of 2 are suggesting. It's a very small probability that you'll die. However, non-seatbelt wearers die significantly more. So I'm saying that to say, don't be thrown off by these very small numbers. Here's the idea about these very small numbers. These small numbers are all greater than 0. All right, so let's kind of write this down. My confidence interval sits between 0.005 and 0.016, but 0 is somewhere over here. All right, so what this suggests is, hey, there's 0. Oops. Here's my confidence interval way to the right of it, or in other words, 0 is not contained in my interval. So what this is suggesting, or what this is saying is, well, your confidence interval is clearly on one side of 0. There is a clear difference between these two proportions. So because my confidence interval does not include 0, it appears that the two fatalities are not equal. The subtraction's one-sided. Why is the subtraction one-sided? Because one number is always larger than the other. And so that means the confidence intervals only includes positive values, and that's because we suggest that the fatality rate is higher for those not wearing seatbelts. All right, what does that suggest about the effectiveness of seatbelts? Well, it suggests that the use of seatbelts is associated with lower fatality rates than non-seatbelt wearers. All right, so that question went by a lot faster, again, because we have the calculator. Let me just look at this question and see if it's any different. So I'm not going to go over question 5 because it's different words, but it's all the same process, and we've gone over the calculator. So there's 9.1.